So let's keep the ideas flowing and welcome our second keynote, who's joining us online from Washington, Dr. Jain. Dr. Jain is currently the Barbara J. Jeremy R. Cox Junior Professor of Computer Science and Engineering at Washington University in St. Louis. He is also a Life Fellow of IEEE, Fellow of ACM, and Fellow of AAAS.
Dr. Jain was one of the co-founders of NANA Networks Incorporated, a senior consulting engineer at Digital Equipment Corporation in Littleton, Massachusetts, and then a professor of computer and information services at Ohio State University. With more than 37,000 citations, according to Google Scholar, Dr. Jain is one of the most highly cited authors in computer science. Dr. Jain has a PhD in applied mathematics and computer science from Harvard University. Live from Washington, let's welcome Dr. Raj Jain.
Thank you. Thank you. It's a pleasure. And so my talk is about quantum versus blockchain. Right now, quantum is happening and blockchain has happened. So the question is, would they go along? And I always make my slides available right up front. So if you have a camera, phone, or whatever, you can scan this QR code and you will get the slides. That way you don't have to worry about taking notes. And the URL will be on every slide. So you can just write it down by hand, or you can go to my website and get it. With that, basically, my talk has 4 parts. First of all, what is quantum? And then quantum bit, because we'll talk a lot about quantum bit. And how can quantum kill the blockchain? Okay. Or why can quantum build the blockchain, and how can we protect? And when will this all happen? By the way, my research is in both areas. I have been working on the blockchain for, I think, at least 6 years. And then we have started on quantum now. So, and we just published our first paper in the IEEE Transactions on Quantum Engineering, which is the most respected journal in quantum. So with that, let's hope that we can get something useful out of this talk. So key strength of the blockchain. Of course, we all know that the blockchain is a chain of blocks, and it has several good properties. Radia already listed some, and I'm going to just list them here again to be complete. It is distributed, so there is no single point of failure. It is decentralized, so the transactions are valid if only agreed by a majority. It is trustless, you don't have to trust anybody. All right. It is cryptographic secure. Basically, the best cryptography that was around in 2008 was used. And it is still the best, actually, in some sense. And the non-repudiation guarantee, everything is signed. So nobody can say, I didn't do that. All right. That's very good. So there are 5 good things about the blockchains. It turns out those 5 good things are also the 5 weak things about the blockchain. So first of all, when we say distributed means everybody can see every transaction. And so one of the exercises I do in my class on blockchain is to go ahead and analyze the Bitcoin blockchain and figure out who has the most money, who has given the money to whom. And you can do that. Everything is public, right? Except that you don't know the name, but you know the number. So it reduces privacy, right? If you have $1 million in the bank, nobody knows that you have $1 million in the bank. But here, somebody knows that somebody has $1 million in the bank, and they're going to look for that person. And that's how the government catches all these Bitcoin thieves, right? Second thing is decentralized consensus. That means that there is no one person who makes the decision. However, it turns out that is only in theory. It turns out as soon as Bitcoin started, there was a big competition, and most of the Bitcoin mining was done in China. This shows what percentage of Bitcoin mining was done in which country. Yellow is China. In about July of 2021, China banned Bitcoin mining. So it became 0, but 2 months later, it shows up again. Okay, so it's still going on. And there is another thing that people don't know about it is that most of these are big companies, and these are, if not big companies, they are part of a pool. So there are only 2 or 3 pools for decentralization of the whole world. Believe it or not, that is very surprising, right? So if 51% of the pools, mining pools, which is very easy to get if you have 80% of the mining being done in one country by 3 companies, then basically that whole point goes away. Trustless. No one is responsible. That's another problem, because you don't trust anybody, you don't know anybody. So I will tell you, I had one experience just once. I bought something with a Bitcoin, not illegal or anything, but just because that company didn't accept anything, international company, other than Bitcoin, and they didn't deliver it. And now I know why they didn't accept anything other than the Bitcoin, because I couldn't do anything. I cannot complain to anybody. Cryptographic security. Now it is based upon public key cryptography. And if somebody can figure out your private key, then they can take away all your money. All right, public key. And so that's why I put this in the blue. And so that getting the private key is like ID theft. And it's very easy to do, by the way. When you get Bitcoin, and you should get some experience, I got the Bitcoin. So I had to buy the Bitcoin from a company. And that company has my private key, believe it or not. And then I had to use a wallet on my phone. And that wallet app could very easily steal my private key. And so there are many opportunities for people to hack you up. So as of December 2017, Wikipedia says that 980,000 Bitcoins have been stolen. And each Bitcoin was, I don't know how many thousand dollars it was at this peak. So this is several billions of dollars have been stolen. Fourth problem with the security is that SHA-256 hash is used as the Merkle tree inside the blocks. Now this is a very technical statement. But what happens is when you write a transaction, all these transactions are put inside the block, and their hashes are used to make sure that the whole in a tree format, so that if any transaction is changed, the whole tree will change, the root of the tree will change. So you don't have to check everything, you just check the root of the tree is correct, right? And the same hash is used as the pointers between the blocks. So again, the same property, that basically the same hash is used to, if a block is changed, you will know. And then same hash is used as proof of work puzzle to determine the winner of the new coins and transaction fees. So basically the same hash is used to figure out who is the winner, and whoever blocks wins, they get 1 coin or some number of coins. Actually not 1 coin would be too much now. The amount goes down with time. But basically, you get a new coin. That's why they call it minter or miners. So they mint or mine the money, mine the gold, mine the Bitcoin, and then they also get the fees, transaction fees. So there is cryptographic security, right? But it is there, it is not there. We don't know. We'll talk about that throughout this talk. Non-repudiation guarantee. So basically, that says you cannot say that I didn't do it. But you can very easily say that somebody stole my private key. So it turns out that the public key, it is also used as public key. So the 2 weak points are public key and hash. All right. So how does quantum come in here? Now the quantum makes those 2 things really weak, because with quantum, it is very easy to factorize large numbers. And the public key and private key are related by basically multiplication. Nobody can factorize very large numbers. If I gave you a 1000-bit number, you would take several years to factorize it. And by that time, my key would have changed. So if somebody gave me a public key, I can find the private key if I can factorize it. Factorize in a big number, right? Anybody with your private key can then start signing your contracts and take your ID away, and they can empty your wallet. So this is one big danger, right? Second danger is easy to invert one-way hash function. So we saw that the hash is used in so many places, and the reason they are used in so many places is because you cannot change anything without changing the hashes. You cannot change anything without changing the hashes. But it turns out that if somebody found an easy way to invert one-way hash function, so they could do that, then they can trivially win the puzzle. So they could just win every mining game, and they could change any transaction, and they could change any block. And the danger is that the quantum computing allows you to do that. The normal computing doesn't allow you to do any of this. So the question is, what is a quantum? So the quantum actually has been around for hundreds of years. Basically, whenever you do A to D conversion, you have to select the smallest amount in A to D conversion. We call it a quantum. So basically, for example, sound, when we started digitizing sound, we take some amount, quantum, and then anything underneath that is either 0 or 1, and then 2, 3, 4, 5, and there's nothing like 3.5. So quantum is always an integer number. And the number of quantums is integer number, the quantum is a fixed size. And what happened was that initially people thought that the light is wave, it is a continuous function, and it's a wave, so it has a frequency, it has a phase, it has amplitude, but that suddenly became not so true. People said, no, a better model for light is that it is discrete. It is not continuous. It is really discrete, and it is really discrete packets of energy that can be absorbed and released, and they called it photon. So you cannot have 1.5 photon. You have to have 1 photon or 2 photons, 3 photons or 5 photons. Only integer numbers of photons you can have in the light. And whenever the electron moves from one orbit to another orbit, it releases or absorbs some photons. So the photons are basically units of energy that you cannot break anymore. So that is the smallest unit of energy, just like here, quantum. So we call them quantum. And the photons, so photons are released, when the electrons move, right? So that is the whole reason behind calling for quantum. And then some people figured out that we can use these photons for computing. So the idea of the quantum bit came in, and it is very complex. I think Radia gave a tutorial yesterday at the conference, half-day tutorial, and you could have actually a whole in our university, we have a whole semester course on quantum. I cannot do that. I will just give you a one slide overview so that at least I can talk about it a little bit more. So the big difference is that in our normal computing, each bit is binary, either 0 or 1. In quantum computing, each bit is not in single digit, it's 2 digits. I mean, 2 numbers. 2 numbers. Okay, it's a vector. It's a vector of 2 numbers. And these numbers are not real even, they are complex numbers. So they have imaginary parts and real parts. Now all that will become very complex. So I didn't use any I or imaginary numbers here. But let's just assume this is a vector which represents a quantum bit. And we call it qubit. Quantum bit is called qubit. Now the qubit has, in this particular qubit, can be written as 3 times 5, 3 divided by 5 times 1, 0, plus 4 divided by 5 times 1, 0, 1. This is what we would call a 0. And this is what we call, this vector would be called 1. And this is a combination of those two. So every bit, whatever value it has, it's a combination of some combination of these two. And the difficult thing is that if you try to measure it, measure how many, what you have, what is in the bit, you cannot measure it. The result would be come out either 0 or 1. And that's the difficulty. And the result will come out 0 and 1 with some probability. It turns out that probabilities are these numbers right here. If you square this number, you get 9 by 25, which is 36%. That is the probability that will come out as 0. And square of this 64%, it will come out as 1. So this particular qubit, if you were to measure it, you don't know what it was before measuring it, but when you measure it, it will not be a complex number like this. It will be either 0 or 1. And with 36% probability, you will get 0. With 64% probability, you will get 1. That makes it difficult, right? So qubit measurement can result in any of its two value, and this is called superposition. So while the bits have a position, they have a position 0 or 1, qubits don't have a position. They can be in two positions at the same time. They can be 1 or they can be 0 with certain probability. And third thing is that if you combine the bits, so let's say you have one bit which is a vector of 2. If you have two bits, that's vector of 4. If you have 3 bits, that is a vector of 8 elements. And then you have 8 probabilities. So here, example of vector of 2 bits, there are 4 probabilities. And they have to add up to 1. Basically, I mean, you have to take a square of this, a square of this, a square of this, a square of this. And that has to add up to 1 because, of course, probability of any combination cannot be more than 1. So this is very probabilistic. All right. So that is the strength and the weakness of quantum. But I think we have enough about quantum. One more very interesting phenomena is entanglement. And I try to explain it in everyday life. You see entanglement happens in your own life. When you or your lover or your partner or your wife, you are probably thinking of one and you call her or him and he says, hey, I was thinking about you too. Okay. Or your friend even, right? And that means that your brains are entangled. They think the same thing at the same time. All right. Opposite can happen too. When you are angry and you're thinking negative about this partner, he or she is also thinking negative about you. So that is also possible. And it turns out this phenomena of entanglement is much more common in the quantum computing than we had thought before. And so what you can do is you can have 2 bits that are entangled, and they will remain entangled even if you put them 1,000 miles apart. That means if you make one as if you measure one as a 0, the other will be measured as 0 as well. If you measure one as 1, it will measure as 1 as well. Or the other way around, where they could be opposite of each other. So if you measure one as 0, the other one will be 1, and you measure as 1, it will be 0. So anyway, so this is really a very strange phenomena that you can teleport the state. You can move the state miles apart very fast, instantly. And so this is called teleportation of a state. And this is used in the quantum key distribution. So when you want to send a key somewhere, your private key, public key, or whatever, you can just use this teleportation entanglement, and the other side will know what keys you are using, right? And this is much more complex than this, but basically entanglement is what makes it interesting. Now, who discovered it? So it turns out in 1935, Einstein wrote a paper in which says this thing is happening, but I think something is wrong with this. So he called it a paradox, and it came out in the New York Times, and I got this copy from actually Wikipedia itself, that Einstein attacks quantum theory. He said something wrong with the quantum theory. How can you have thing which can move at the speed faster than light? Now this is thing. Einstein clearly showed that E is equal to mc square. Nothing can go faster than light. And here suddenly there is a phenomena that he himself saw, and it requires that the state move faster than the light. But it happens because after 30 or 40 years, somebody physically showed that, yeah, this is possible to do that. So it's not just a theory. Up until this point, it was a theory. Then in 1967, they produced entangled photons, and they can say, oh, look, it happens. And then in 1984, somebody said, well, if this happens, then we can just use it for the distribution of information. And then this year, the Nobel Physics Prize is for this phenomena, exactly this phenomena, entangled photons. So the 3 scientists who got Nobel Physics Prize this year, they got it because they did their work on entanglement. All right. So this is a very interesting topic and very hard topic. So what else can you do? Another thing that is, before we get onto the security part, is quantum random number generator. So generally what happens is when you want to generate a key or you want to do anything, you need a number that cannot be repeated. Then, you just use a pseudo random number generator. But the problem with the pseudo random number generator is that they can be easily broken. So you really need a true random number generator. And Some people use, heat or thermal or something, but even those things are correlated. I mean, the heat cannot change in a microsecond. So basically, so those are not truly random. They have a bias too. But with quantum, you can get true random numbers. So some people have made business out of it. Actually, there is a company called ID Quantique that supplies a chip based upon this phenomena and called quantum random number generator. And in fact, Samsung uses this chip in their Galaxy phones. And so basically, this is at least a practical example of where the quantum phenomena is being used for something which is useful today. Now let's go back to the factorization issue. So if you want to factorize a large number, let's say capital N is a large number, you have to divide it by 1, 2, 3, 5, 7, 9, all the primes until the square root of n to see if it is a prime or not. If it is not a prime, what is the factor? And that's a very long process, right? And it turns out there is no general purpose factorization algorithm for integers on the classical computers. In 2019, a group of scientists factored a 240 digit, which is 795-bit number, which is used in RSA240, using 900 core years, which basically says how much computing power they took. They use 900 cores for 1 year, or you can just 450 cores for half year or whatever, 2 years. But anyway, so RSA 1024 will take 5,000 times longer, 500 times longer, because this is even a longer number, bigger number. This is smaller number. This is 240 digits, right? So most difficult to factor are products of two primes of similar size. So the problem is that if your two factors were very close to square root of n, you would not find it until you reach square root of n. So that is what we use as private key, public key, something which is very large. In 2020, RSA 250 was broken using 2,700 core years, using a very optimized algorithm. So that is how long it takes for somebody to break 250, and we don't even use 250, that's old, right? No published algorithm can factor a b-bit number in order of b raised to k time. That means there is no polynomial time algorithm using classical computing. Okay. However, in 1994, Shor published an algorithm to factorize in polynomial time on a quantum computer. All right, all these previous statements were for the classical computers. But if you had a quantum computer, then you could do in polynomial time, not only polynomial in log n. That makes it a big difference, right? Log n. And so the world got worried. In 1994, really, the quantum computing took off because of this paper. Because people said, hey, if you can do that thing, why not we make them? And here is the algorithm. This guy, Peter Shor, who actually studied at MIT and is now a professor at MIT, he wrote an algorithm to find the prime factors of numbers exponentially faster than conventional computers. And it's very simple, 2 steps. First step is you want to find when a raised to I mod n will become equal to 1. A raised to p mod n will become equal to 1. And if you find that number p, then you can find the 2 factors right there. Okay, so a is a co-prime to n, where a has to be co-prime. So a cannot be something that is already factor of n. All right, this is greatest common denominator, GCD of a and n has to be 1. And second step is that once you find p, then the factors are GCD of n comma a raised to p by 2 plus 1 and GCD of n comma a raised to p by 2 plus 1. Of course, p has to be even number. If p is odd, then that's not a good choice because this will not be an integer. In that case, you go back and try another a. All right, I will give an example. And this is the only example you will read everywhere if you read quantum computing. N is equal to 15, a equal to 2. And now 2 is prime to 15. It is not a factor of 15. But you write down 2 is equal to 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, mod 15, right? 2 raised to 4 mod 15 is 1. 2 raised to 4 is 16, mod 15 is 1. And therefore you found the p equal to 4, And therefore, the factors are p by 2, 2 raised to 2 by 2 plus 1 and 15, 2 raised to 2 minus 1 and 15. And this is 4 plus 1, 5 and 15. What is the common factor of 5 and 15? Is 5. And what is the common factor of 3 and 15? Is 3. So there you go. You factorized without going through this whole business of square root of n business. This is more like polynomial in log n. All right. So this is the key thing. And then second problem is the hash function. Problem with the hash function is the hash functions are used in all database searches. When you want to put something in some place in a table, you hash the key and you find the location. And it produces a fixed size. So the result of the hash function is basically something that is between 0 and n or 1 and n. So you know the location where to go to store it or where location to find it. It should be easy to compute, because if it is very difficult to compute, then you really can't use it for frequency accesses, right? And it should be pseudo random, so that it distributes informally over the table. So if it is not pseudo random, everything might just end up here, and you don't want that. You want it to be distributed all over. So that is a hash function, and we have had hash function for a long time. And when the security people came around, they started using hash functions for security, but they put 3 more restrictions on it. First restriction, that it has to be one way. That means you can go in, but you cannot come out. One way. You can compute the hash, but you cannot invert the hash. Very difficult to find x given hx. If somebody gave you hash, you cannot find x. Second condition is that it is not possible to even find y which hashes to the same value. So if somebody gave you x, you can hash it, get the hx, but you cannot find another y which will hash to the same value. So you cannot replace x with y, like in the transactions or in the in the blocks. Third thing is strong collision resistant. That means you cannot find any two x and y's. So this is actually a stronger condition than the sixth condition, that will hash to the same value. So if you can find something which is this way, which is very one way and does that, that is a cryptographic hash function. And we have many of them, by the way. In particular, SHA-256 that I mentioned so many times is a collision resistant cryptographic hash function, right? And that is why it was selected by Bitcoin and is used everywhere else. So the hashes are one way. Given them, you cannot find the inverse, and the inversion is used as a puzzle. You see, that is why they even use as a puzzle, because basically the puzzle that you miners have to do is to find a number that will hash to a value below the limit. They give you a limit. They say, okay, you should any number which is, this is the limit. And if you find the number that hashes to below that limit, you won the game and you won the coin, right? So this is because you cannot invert that. So you really have to keep trying 1, 2, 3, 4, 5 like that. And Bitcoin miners try to find that X such that when they can do it under the limit. And the difficulty increases and is decreased. So what happens is, as the time goes by, the computers become faster. Nakamoto, the inventor of Bitcoin, has already thought about that, and he says, okay, we will make it harder and harder for people to invert by reducing the range. So all we are trying to do is, can you get me a number that hashes to this range, not to just exact value, just between the 0 and that number. So as the computing power increases, the Bitcoin difficulty increases. Every 14 days they increase it, and requiring more and more computing energy. And this applies to all other blockchains that use proof of work. And proof of work means that basically proof of work means that please prove that you have enough capacity to do the work. Prove that you have enough computing capacity to do the work. And this has been criticized a lot, and you heard in the previous two speakers talk as well. So here comes Love Kumar Grover from IIT Delhi. Love Kumar Grover, a graduate of IIT Delhi and a PhD from Stanford, he invented something called quantum mechanical database search algorithm. So he says that, well, you can just find where the data is by inverting a hash. So if you are looking, see, the thing is, we are talking about storing the data, right? But now he's saying you can even search the data by, suppose somebody gave you the data, you can just invert the function and you can get the data using order of a square root of n operations. where n is the size of the table. So can invert any hash in order of the n, order of a square root of n operations. And the classical computing takes order of n operations. That's the difference. Now, how much is that difference? A miner can solve a SHA-256 puzzle. They will need 2 raised to 256 operations using normal computers. But with quantum computers, they can do it in 2 raised to 128 trials, right? And that difference of 2 raised to 128 is 10 quadrillion. That is 10 raised to 16 times faster. And that will save a lot of money to the miners, a lot of electricity, and a lot of everything. But basically, everybody will be able to solve it, and that's not very good. So hacker can find a collision in 10 quadrillion times faster and makes changing the transactions and blocks a 10 quadrillion times faster without affecting the hash values. Now, if this started happening, then everything in the blockchain will become 10 quadrillion faster. I mean, not everything, basically the frauds, the stealing, the changing, the security will go away. So how to protect? So the question is, how do we protect quantum resistant blockchains? So there are two things which are happening. First of all, people are working on blockchains that will not be affected by quantum. Yeah, and so NIST, which is the National Institute of Standards and Technology in the United States, they ran a competition several years ago. Now they have results. This year they have announced that this is the algorithm that everybody should use. They recommend this one for encryption and key establishment, and they recommend 3 different ones for signatures. So these things are already here, and you can use them whether you use blockchain or not. Even if you just do normal encryption and normal signatures, you can use them, right? They don't require the computing. They just work with the normal computing. All right. Another thing you can do is use secret key cryptography. So secret key is not factoring. It doesn't have private key and public key. It's just one key. And if you can do that, then that is also strong. Third thing you can do is we just large hashes. SHA-512, for example, instead of 256. If you use 512, then the square root of 512 would be basically that 256. So the difficulty will remain the same as it is today on the, basically with the quantum computers. So hashes can be simply taken care of by using larger hashes, and the cryptography can be taken care of by simply using better cryptography. And that is being done. Then there are people like us, like my students, they're working on quantum native blockchains. So they are trying to see what can we do in the classical, in the quantum computing itself. Why do we have to classical computing, right? And the problem is that you cannot really do anything in pure quantum computing. Even in quantum computing, you need classical computing and you need classical communication lines and all that. It's a long story. I would not go into that, but basically all the classic quantum computing circuits are combination of classical plus quantum. All right. So now the question is, what is wrong with the quantum? I already told you what is wrong with the blockchain. So now the question is, anything wrong with the quantum? Yes, plenty. First of all, decoherence. The qubits lose their state over time. So they are not stable. Like, we know how to store a 0 and how to store a 1, but we really don't know how to store a qubit. Right now we haven't invented that. And whatever we keep, it actually disappears because it depends upon the temperature, it depends upon the environment. And so you have to keep it at a very low, almost 0-degree temperature, 0 Kelvin temperature. And right now the lowest they can get is 10 millikelvin. So you need, large cooling equipment, right? And need extra qubit, and even then it will disappear. So you need to keep error correction and large number of bits because the error rate is very high. So it can be as high as 1,000 times more qubits to take care of the errors. So most of the research that you read right now today on quantum is theoretical. Practical experiments are limited to a tiny number of qubits. Because even 1 qubit, 2 qubit is difficult, let alone, thousands of qubits. All right. In fact, there's an article very recently in IEEE Spectrum, the case against quantum computing. Those of you who want to read it can read that. Then there are more challenges. How to make quantum computers. And the most, after trying out many different methods, and actually in my previous presentations, I used to have a list of 7 different methods that we don't need anymore because most companies have now come down to this algorithm, interconnected Josephson junctions, which was developed by D-Wave Systems, now used by Intel, IBM, Quora, Google. Everybody uses that. However, everybody's at a different point in time. Basically, IBM is ahead, and this month they announced, or last month they announced that they have a 433 qubit computer. This is their largest quantum computer, 433 bit. However, you need 1,000 or 10,000 qubit computer to do anything interesting right now. You see, 1,000 qubits will require 2 raised to 1,000 parameters. Remember that 2 qubits required 4 parameters. 3 qubits required 8 parameters. 1,000 qubits will require 10 raised to 300 parameters. And the people who are against quantum, they said, well, that is more than the number of subatomic particles in the observable universe. So it is not the world. In the whole universe, it is not the atoms, it's the subatomic particles. So that's a very large number. So basically, how do you reduce that? Well, you don't have to have complete independence, and there are ways to reduce that, and people are working on that. So this is other problem. And here is the difference you can see. So this is a quantum computer, the latest one, 433 bit, IBM's Quantum System 1, 2019. And this is a traditional computer, 1943 ENIAC. They're same size. This is ENIAC in 1943. It didn't really have any storage. It only had registers. There were 20 registers each, and this was a decimal machine, not a binary machine. And each digit was 10 decimal, each register was 10 decimal digits. Similarly, this one, has 20 qubits and it has 9 feet cube. So 9 feet by 9 feet by 9 feet. It's a big room. And so is this. So this is where we are. If you want to compare the classical computing and the quantum computing, you know that we have a long way to go, 43 to 2019. After 60 years, or maybe 80 years, we are where in the traditional computing. And so here we will not take 80 years to get there. But what will happen is the technology moves exponentially fast, but it will take quite some time to get to where we are in the regular computing. So what we do is in our research, and we are doing research, we just kind of have to use the simulators. So we have many simulators, access to many simulators, and luckily most of these are not expensive, or actually most of them are free. So you can select one of the simulators and you can start working with the qubits, and that's what most papers that talk about qubit do. They just use the simulator to get the results, whatever they want to get. Now, finally, what is happening with the Shor's algorithm? Well, Shor published the paper in 1994, but nobody really implemented it. In 2001, IBM was able to factor 15, the number 15, with a 7-qubit computer. The first number that was factored with Shor's algorithm was number 15. I just showed you that number, right? You could do it on the palm of your hand, but we needed a 7-qubit computer that required at least 7 years of work from 94 to 2001, right? In 2012, they did the same number again with a better computer, solid state qubits. And 2012, okay, well, actually they not only got 15, they also got 21. They could factorize 21, wow. In 2019, they tried to factorize 35, but failed because the errors, because of the decoherence I talked about. So this is where we are right now, 2019. The largest number you can factorize is 35, right? The quantum circuit for Shor algorithm, and another problem is that it is not just you use the same computer to do everything. No, it has to be custom designed for each choice of n and each choice of a. So you need 2 qubit registers where q is log base 2 of n. So you can see if you have those big numbers that we were talking about, it will take quite a bit of time before we get there. So that's the good news. And then we'll talk about what is happening in the real world. So I went to Gartner, and here's what Gartner says, that what is happening in the real world. So basically, the way you read this graph is that whatever is technologies are here in this part of the thing, they are research and startup. Not much is basically not much money to be made here, but there is basically research to be done. This is the middle part, highest top of the hype. This is where if you are, then you make a lot of money by selling your company to a big company. So D-Wave, for example, made a lot of money by being in quantum computing, which is at the top of the hype. Once it is sold to the big companies, the profits go down. And then the technology moves to countries where the manufacturing is the only way you can make profit. The technology profits are here. The manufacturing profits are here. The invention profits are here. And the research, satisfaction is here. Actually, you don't make any profit in the universities like us, but you get satisfaction of doing something good, right? So that is where we are. The quantum computing is at the top of the hype. However, this triangle means that it will not happen for 10 years. So they estimate that this will take 10 years. Now, so Gartner doesn't know the truth either. Okay. But what they do is they try to ask people, and then based upon that, they just say whatever they say, and they have been wrong, just like everybody else. But this is what they're saying right now is that you don't have to worry about all this for 10 years, but they're saying that get ready for all that. So this is one message. All right. That brings me to the end of my talk. And there are 8 key points that I wanted to bring up. First is the quantum computing is based upon the discrete nature of photons. So what is a quantum? Quantum is a photon, and photon cannot be divided. It is just you can have 1 photon, 2 photons, 3 photons. So that is why we call it quantum. And then the qubit indicates the state of the photon. And n qubits is represented by a vector of 2 raised to n complex numbers. So actually, it is very difficult to represent quantum computing in traditional ways. And so that is what it shows is that very complex number would be, and not only complex numbers, but also a large number of complex numbers just for n qubits. Quantum has several interesting phenomena such as entanglement that can be used for teleport information or link blocks. Shor's factorization algorithm allows factorization in less time than classical computing. Grover's algorithm helps invert the hashes in much less time than the classical computing, and the blockchains can be broken by these algorithms. However, there are 2 things that save us. First, quantum safe crypto is in standardization, which is good. It already happened. Fortunately, it is easy to make sufficient, it isn't easy to make sufficiently large quantum computers at this time. So it is not possible for Shor's algorithm or Grover's algorithm to have any impact on this generation of blockchain. And I put this word, this is very important to notice. This generation of blockchains, 2008 to 2028. Why? Because one generation lifetime is 20 years. My son is 20 years younger than me, and my father was at least 20 years older than me. So 20 years is one generation, and most technologies survive for one generation, and then they're taken over by some other generation, just like life. Okay, so the cars were taken over by whatever, I don't know, the train were first, a car. Maybe trains were first, then the cars took over, and the planes took over, and then whatever else came on. So every generation, there is a new thing. We already know in 5G, 4G, 3G, the technology moves, but that G actually moves every 10 years. So nothing stays constant for more than 10 to 20 years, because if it stayed constant, something will come over and say, hey, you got to change it. And that is already happening in the blockchain world. I mean, basically, Ethereum is getting more currency because of its different approach to consensus and active in development right now, as opposed to Bitcoin, which is sort of more frozen in time. So slowly things are moving around. And so this is now my guess that after a few years, Bitcoin, the blockchains may be there. It's not that blockchains will go away, but it will be different generation of blockchains, like very fast trains. The trains are not the same today that used to be 20 years ago, or it's not the same locomotive, the steam engines that we used to, do when I was young. So things change. Sometimes they change the name, sometimes they don't change the name. So this generation of blockchains has maybe few more years left. That is the end of my talk. And I would really appreciate any questions from the audience, please. I think I still have time. My talk basically had given me, I think, 40 minutes. Yeah, 40 minutes. And I don't think I have taken that. But if I have not taken, then please ask questions. And it will be time check, 1 minute left. Okay, all right. So I'm done. So if there are any questions, please ask now. Otherwise, we can be done. Oh, actually, there's one more slide I want to show you. Last slide. That is again the slide, how you get the slides. So this is the slide. So time check. Okay, so if there are no questions, are there no questions? Please, host, please let me know. And then we can all go for coffee break.
Thank you, Dr. Jain. You probably can't hear me. Can you hear me?
I can hear you.
Oh,
yeah.
Thank you for sharing. I think if anyone has any questions for Dr. Jain, you can save it for the panel session. There'll be an audience Q&A part. So let's take a break, take a 10 minutes break, and enjoy some coffee and snacks just outside the ballroom, and then we'll be back in 10 minutes. Thank you.